Somewhere beneath your feet, the earth is alive with heat. Before we go any further, if you want a brand new earth topic every single night to fall asleep to, subscribe. One tap and a new story is waiting for you every evening. That heat has been there since the very beginning. When our planet first formed, about 4.5 billion years ago, it was a molten ball of rock and metal. Slowly, over vast stretches of time, the outer layers cooled. They hardened into the ground we walk on. But deep below, the heat never left. Picture the earth from far above. You see the blue of the oceans, the brown and green of the continents, the white swirl of clouds drifting slowly across the surface. It looks still from up there, peaceful, but beneath that calm surface, an enormous engine is running. It has been running without pause for longer than any mind can truly hold. The core of our planet sits at the very center, roughly 4,000 miles below your feet. Scientists believe the inner core is solid iron and nickel, squeezed so tightly by the weight of everything above it that it cannot melt. The outer core surrounding it is liquid metal. It churns and flows in slow, powerful currents. That movement generates Earth's magnetic field, the invisible shield that protects all life from the harshest rays of the sun. Above the core lies the mantle, that thick layer of hot rock between the crust and the core. The mantle is not quite liquid and not quite solid. It behaves more like very, very slow putty. Over millions of years, it creeps and flows. It carries heat upward from the core toward the surface. In certain places, that heat finds a way through. Those places are where geysers and hot springs are born. A geyser is a rare and remarkable thing. It is a vent in the Earth's surface that shoots a column of boiling water and steam high into the air. Some geysers erupt in tall, roaring towers. Others send up soft, quiet plumes that drift away on the wind like pale smoke. Either way, what you are watching is the planet breathing. Heat from deep inside the earth, rising up through rock and water, finally breaking free into the open sky. Hot springs are gentler cousins to geysers. They form when groundwater seeps down through cracks in the rock, gets heated by the Earth's warmth below, and rises back up to the surface. The water pools in basins of vivid color, steaming softly in the cool air. Some hot springs are barely warmer than a bath. Others are near boiling. A few are hot enough to cook an egg. There are only about 1,000 geysers on the entire planet. That sounds like a lot, but spread across the whole surface of the Earth, it is a very small number. More than half of all the world's geysers sit inside one place, Yellowstone National Park in the western United States. Yellowstone holds roughly 500 geysers within its borders. It is one of the most geologically active places on the surface of our world. Stand at the edge of Yellowstone's Norris Geyser Basin on a cold morning. The ground around you is pale gray and white, crusted with minerals left behind by thousands of years of rising water. Steam drifts up from dozens of vents in the earth. The air smells faintly of sulfur, that sharp, clean scent of deep rock chemistry. The ground itself feels warm underfoot. You can hear the low hiss and gurgle of water moving through hidden channels far below. It is one of the most quietly astonishing places on Earth. What makes geysers so rare is that they need a very specific set of conditions to exist. They need heat. They need water. They need a certain kind of rock that holds pressure without cracking in the wrong places. They need a plumbing system built over thousands of years that works in just the right way. Change any one of those things, and the geyser never forms at all. The fact that they exist at all feels like something close to a small miracle of geology. And yet here they are, scattered across Iceland, New Zealand, Chile, Kamchatka in Russia, and above all, Yellowstone. Each one a window into the deep interior of a living planet. Each one a reminder that the ground beneath us is not dead rock. It is warm. It is active. It has been working quietly, steadily, for longer than life itself has existed on this world. The heat below is patient, and tonight we are going to learn its story. So let us start at the beginning. Let us start with what a geyser actually is. A geyser is a hot spring that erupts. That is the whole idea in its simplest form. Somewhere underground, water heats up past its normal boiling point. Pressure builds, and then, with a deep rumble and a rush of white steam, that that water bursts upward through a narrow opening in the rock and shoots into the open air. It is a release, a long, slow breath held deep in the earth, finally let go. Most hot springs never erupt at all. They simply sit there, steaming gently, their water rising to the surface in a slow, quiet flow. A geyser is different. A geyser builds pressure. It waits, and then it goes. The word geyser comes from an Icelandic word, Geysir, which means to gush. That original geyser, the one that gave its name to all the others, still exists in Iceland today. It is called Geysir, and it has been erupting on and off for thousands of years. When early Icelandic settlers first saw it, they had no framework to explain what they were looking at. Just a hole in the ground that roared and threw boiling water 50 feet into the sky. It must have seemed like the earth itself was breathing. To understand how a geyser wakes up, picture a long, winding tube of rock. This tube reaches deep underground, sometimes hundreds of feet down, where the rock is extremely hot. Groundwater, which is rainwater and snowmelt that has slowly soaked into the earth, trickles down into this tube over many years. As it sinks deeper, it gets hotter. At the surface, water boils at 212 degrees Fahrenheit, but deep underground, where pressure from the weight of all that rock and water above presses down hard, the boiling point rises. Water can reach 250, even 300 degrees Fahrenheit down there, and still stay liquid. It is superheated, meaning it is hotter than boiling, but held in a liquid state by the pressure around it. Now the tube is full of this extremely hot, pressurized water. The water near the top of the tube is slightly cooler. It acts like a lid, holding the pressure down, but the water at the bottom keeps getting hotter. The pressure keeps climbing. At some point, the water near the top starts to boil just a little. That releases some pressure, and that small release is enough to trigger the water below it to flash, almost instantly, into steam. Steam takes up about 1,500 times more space than liquid water. That expansion has nowhere to go but up, and so the geyser erupts. The whole column of water blasts upward through the narrow opening in the rock, shooting steam and boiling water high into the air. A small geyser might send water 10 or 20 feet up. A large one can throw a column of water and steam more than 300 feet into the sky. That is taller than the Statue of Liberty, taller than a 30-story building, and it happens in seconds. After the eruption, the tube is mostly empty. Cooler groundwater begins to seep back in. The long, slow process of filling and heating starts again. Some geysers refill and erupt within minutes. Others take hours. Old Faithful, the most famous geyser in Yellowstone National Park, erupts roughly every 90 minutes. Give or take. Scientists have studied its rhythm for over 150 years and can predict its next eruption to within about 10 minutes. That kind of regularity is rare. Most geysers are far less predictable. What makes the whole process so delicate is how many things have to go exactly right. The tube must be narrow enough to build pressure, but open enough to let water flow in. The rock around it must be strong enough to hold that pressure without cracking and releasing it sideways. The heat source below must be steady. The water supply from above must be consistent. If any one of those things shifts, the geyser changes. It might slow down. It might stop entirely. It might never erupt again. This is why geysers are so rare. There are only about 1,000 active geysers in the entire world. Of those, roughly half are found in Yellowstone National Park. The rest are scattered across a small number of places where the conditions happen to line up just right. In a world covered by land and ocean, 1,000 geysers is almost nothing. They are small, precise, and extraordinarily specific. Each one the result of thousands of years of slow, patient geology, working in quiet coordination beneath our feet. That slow, patient geology has a very specific shape. Deep underground, beneath every geyser and hot spring on Earth, there is a system of cracks, channels, and chambers carved into solid rock. Scientists call this the hydrothermal plumbing system. It is not a single pipe or a neat tunnel. It is more like a tangled root system, spreading through the rock in ways that took thousands of years to form. It begins with water. Rain falls. Snow melts. That surface water seeps down through the soil through cracks in the bedrock, deeper and deeper into the earth. This process is called infiltration, and it is remarkably slow. A single drop of rainwater that falls in Yellowstone today might take hundreds of years to work its way down to the depths where the heat lives. It travels through tiny fractures in the rock, moving inch by inch, pulled downward by gravity and drawn forward by pressure. As it descends, the rock around it gets hotter. The Earth's interior is always warm, but in places where volcanic activity sits close to the surface, that warmth becomes intense. The water absorbs heat from the surrounding rock as it moves. By the time it reaches the deepest parts of the system, it may be sitting in temperatures well above the normal boiling point of water. At sea level, water boils at 212 degrees Fahrenheit, but deep underground, the weight of all that rock above creates enormous pressure. That pressure keeps the water liquid even at temperatures of 400 degrees Fahrenheit or more. The rock is essentially squeezing the water so hard that it cannot turn to steam, no matter how hot it gets. This superheated water then begins to rise. Hot water is lighter than cold water, so it naturally moves upward through the cracks and channels in the rock. As it climbs, the pressure around it decreases. And as the pressure drops, the water gets closer and closer to its boiling point. In a hot spring, this rising water reaches the surface while still mostly liquid, spilling out gently into a pool. In a geyser, the geometry of the underground channel is different. The tube narrows at some point, trapping the rising water below that narrow section. Pressure builds. The water at the bottom gets hotter and hotter. And then, when the pressure finally overcomes the resistance, the whole column of water above it flashes into steam and launches upward. The rock itself plays a huge role in all of this. Not just any rock will do. Geysers form most easily in a type of volcanic rock called rhyolite, a pale, fine-grained stone that forms when thick, silica-rich lava cools slowly. Rhyolite is important because it contains a mineral called silica, and silica behaves in a very specific way when it dissolves in hot water. As the superheated water moves through rhyolite, it slowly dissolves tiny amounts of silica from the rock. When that water eventually cools near the surface, the silica comes back out of solution and deposits itself on the walls of the underground channels. Over thousands of years, this creates a smooth, glassy lining inside the geyser's tube. That lining, called sinter, is what makes the tube strong enough to hold pressure without cracking apart. Without it, the whole system would leak sideways into the surrounding rock, and the geyser would never build enough force to erupt. This is why geysers are so rare, even in volcanic regions. The rock has to be the right kind. The water chemistry has to be right. The heat source has to be positioned at the right depth. And all of this has to stay stable for long enough that the silica lining can form and strengthen. Scientists estimate that a fully developed geyser plumbing system can take anywhere from a few hundred to several thousand years to mature. The geyser you watch erupt today is the result of a process that may have started before any written human history existed in that part of the world. There is something quietly remarkable about that. The water rising through the rock right now began its journey as snowfall on a mountain slope centuries ago. The channel it travels through was carved grain by grain, mineral by mineral, over a span of time that dwarfs any single human life. The heat driving it upward comes from magma that has been cooling slowly since long before the first person ever stood at the edge of a hot spring and felt the warm mist on their face. Every eruption is the end of a very long story, and the next eruption is already beginning deep in the dark, where the water is gathering heat and the pressure is slowly, steadily building again. Old Faithful sits in Yellowstone National Park in the western United States. It is perhaps the most recognized geyser on Earth. People have been watching it erupt since the 1870s, and it has never truly disappointed them. Every 60 to 90 minutes or so, it sends a column of boiling water and steam somewhere between 100 and 180 feet into the air. That column glows white against the blue Wyoming sky, and then it falls, and the crowd goes quiet, and the ground settles again. But Old Faithful is not alone. Yellowstone holds more active geysers than any other place on Earth. Scientists have counted over 500 of them within the park's boundaries. That is more than half of all the active geysers in the entire world, gathered in one high plateau in the American West. The park also contains roughly 10,000 thermal features in total, including hot springs, mud pots, and vents that hiss and steam without ever erupting at all. Walking through that landscape feels like standing on the skin of something alive. Old Faithful belongs to a group of geysers clustered in what is called the Upper Geyser Basin. Its neighbors each have their own personalities. Castle Geyser builds a wide cone of pale mineral deposits that looks like the ruins of a small fortress. Grand Geyser erupts in tall, surging bursts that can reach nearly 200 feet. Riverside Geyser sends its spray arching out over the Firehole River at a gentle angle, like a fountain tipped sideways. Each one follows its own rhythm, shaped by the unique geometry of the plumbing system below it. The material that lines those underground channels is called silica, and it comes from a mineral called silicite, or more precisely, from a form of dissolved silicon dioxide that the hot water carries up from deep rock. Silicon is one of the most common elements in the Earth's crust. It was forged inside ancient stars billions of years before our solar system existed. When those stars burned out and collapsed, they scattered their contents across space. That scattered material eventually gathered into clouds of gas and dust. Gravity pulled those clouds together. Over millions of years, they formed the sun, the planets, and everything on them, including the silica now lining the walls of a geyser deep beneath Yellowstone. The water itself carries a similar story. Earth's water did not all form here. Scientists believe a significant portion of it arrived from space, carried by icy comets and water-rich asteroids that bombarded the young planet billions of years ago. The hydrogen and oxygen in that water were also forged in stars, or in the case of hydrogen, in the very first moments after the universe began. The water now rising through a geyser vent may contain atoms that are nearly 14 billion years old. It is ancient beyond any easy measure. As that water moves through the rock, it picks up minerals along the way. It dissolves silica, as we have seen. It also collects calcium, sodium, sulfur, and traces of many other elements. When the water finally erupts and cools at the surface, it deposits those minerals back down, slowly building the pale, chalky formations that surround geyser openings. This material is called geyserite, a form of silica that accumulates in thin layers over many decades. The smooth, scalloped edges of a geyser cone are built grain by grain, season by season, the same patient process that carved the underground channels below. Old Faithful's cone is not especially dramatic to look at. It sits low and wide, a modest mound of pale gray and cream-colored geyserite. But that understated shape holds centuries of eruptions within it. Each layer of mineral deposit is a record of the water that passed through, the heat that drove it, and the time that shaped it. Geologists can sometimes read those layers the way others read tree rings, finding in them a slow history of activity and change. What makes Old Faithful so reliable is the relatively simple shape of its underground chamber. The water fills, heats, and releases in a fairly consistent cycle because nothing in its plumbing is especially complicated or prone to blockage. Other geysers in the basin have more tangled systems, and their eruption schedules are far less predictable. Reliability in a geyser turns out to be a matter of elegant design below the surface. Every geyser field on Earth is its own collection of individual stories, each one shaped by local rock, local heat, and local water. But all of them share the same deep ingredients: ancient minerals, ancient water, and heat that traces its origins back to the formation of the planet itself. The building blocks are the same everywhere. Only the arrangement differs. Now look closely at the water itself, not at the steam rising above it or the rock surrounding it, but at the water. Because in a hot spring, the water is rarely just blue or clear. It glows. It shifts. It holds colors that seem almost impossible for something that comes from the ground. The colors in a hot spring are alive. They come from living things, microscopic organisms called thermophiles, which means heat lovers. These tiny creatures thrive in water that would kill almost anything else. They form dense around the edges of hot springs, and those mats carry color. Brilliant orange, deep red, pale yellow, bright green. The color depends on the exact temperature of the water in each zone. The most famous example of this is Grand Prismatic Spring in Yellowstone National Park. It is the largest hot spring in the United States and the third largest in the world. It stretches more than 300 feet across, roughly the length of a football field. From above, it looks like a painting. The center is a deep, clear blue. Moving outward, the colors shift through green, then yellow, then orange, then a rich brick red at the edges. Each ring of color marks a different temperature zone, and each zone holds a different community of life. The deep blue at the center comes from the water itself. The spring there is too hot for most life, reaching temperatures above 185 degrees Fahrenheit. At that heat, very few organisms can survive, so the water stays clear, and the blue comes from the way sunlight scatters through pure, very hot water. It is the same reason the deep ocean looks blue. The heat keeps the center almost sterile, almost empty, but move toward the edges where the water cools slightly and life rushes in. Cyanobacteria, a type of ancient microorganism that has existed on Earth for billions of years, begin to appear. Different species of cyanobacteria contain different pigments, the natural chemicals that give them their color. Some carry orange and red pigments to protect themselves from intense sunlight. Others carry green pigments used to capture light for energy. The temperature of the water determines which species can survive, and the species that survive determine the color you see. This means the colors of Grand Prismatic Spring are not decorations. They are a map of invisible forces. Heat pushes outward from the center. Life pushes inward from the edges. The two forces meet in a slow, constant negotiation, and the result is those rings of color, shifting and deepening with the seasons. In summer, the orange and red rings grow brighter because sunlight is stronger, and the pigments that protect against it become more concentrated. In winter, the colors soften and fade slightly. The spring breathes with the year. The same forces shape every hot spring, though not always in such dramatic fashion. Minerals dissolved in the water also add color. Iron compounds can stain the surrounding rock in shades of rust and amber. Sulfur deposits leave pale yellow crusts near the edges of pools and along the channels where water flows. Silica, the mineral that builds geyserite, can give the rock around a spring a pale, almost white sheen. Each mineral tells you something about the chemistry of the water and the rock it passed through on its way to the surface. The heat itself is a force that shapes everything it touches. As hot water rises and meets cooler air, it deposits its dissolved minerals along the way. Over decades and centuries, those deposits build up into terraces, shelves, and rims of stone. Mammoth Hot Springs in Yellowstone is one of the most striking examples. They're hot water rich in calcium carbonate, a mineral also found in chalk and limestone, flows over a hillside and slowly builds white and cream-colored terraces that look almost like frozen waterfalls. The water is still flowing. The stone is still growing. It is a slow sculpture, built one thin layer at a time. What ties all of this together is pressure. The pressure of the water column above, the pressure of the rock surrounding the underground chambers, the pressure of heat pushing upward from below. These forces do not shout. They work quietly over enormous stretches of time, shaping the rock, guiding the water, and sorting the living things into their temperature zones with calm precision. The result is a system of extraordinary order, written in color and stone. The hot spring does not try to be beautiful. It simply obeys the forces acting upon it. And in that obedience, it becomes one of the most vivid things on Earth. Now consider what lives inside that vivid, boiling world. Most of us picture a hot spring as a place where nothing could survive. The water is scalding. The chemistry is strange. There is no shade, no shelter, no soil. And yet, hot springs are among the most densely packed living environments on Earth. They are home to some of the oldest and most resilient life forms our planet has ever produced. These living things are called extremophiles, which simply means organisms that love extreme conditions. They do not merely tolerate the heat, they require it. Take them out of the boiling water, and they die. Put them in a cool stream, and they are as lost as a fish dropped on dry land. The hot spring is not their prison. It is their home. The most ancient of these creatures are called archaea. They are single-celled organisms so small that 1 million of them could fit across the width of a human hair. Scientists believe archaea were among the very first living things on Earth, appearing roughly 3.5 billion years ago, when the young planet was still covered in volcanic heat. In a sense, the hot spring is not a harsh environment for them. It is the original one. It is what life looked like at the very beginning. To understand just how small these creatures are, think of it this way. If a single archaeon were the size of a marble, a human being would be roughly as tall as Mount Everest. That is the scale of the difference. These organisms are almost impossibly tiny, and yet they drive entire ecosystems. They break down minerals. They release gases. They feed other microbes, which feed other organisms in turn. The whole chain of life in a hot spring begins with something you could never see with the naked eye. Some of these microbes live in water that reaches 121 degrees Celsius, which is hotter than boiling water at sea level. Normal boiling happens at 100 degrees Celsius. These organisms push past that threshold entirely. Scientists call them hyperthermophiles, meaning they thrive at temperatures that would destroy most proteins and dissolve most cell structures. Their chemistry is built differently. Their proteins are folded in ways that lock tight under heat rather than falling apart. They are, in a quiet way, a kind of biological marvel. The colors you see in a hot spring are often these microbes made visible. A mat of yellow, microbes near the hottest center of a spring, might be only a few millimeters thick, but it can contain billions of individual organisms packed together. Move a few feet toward the cooler edge of the spring, and the color shifts to orange, then green, then brown. Each color band is a different community of life, sorted by temperature, the way books are sorted by subject on a shelf. What looks like abstract art from a distance is actually a precise map of who can live where. One of the most important discoveries in modern science came from a hot spring. In the 1960s, a scientist named Thomas Brock was studying the bright yellow and orange mats in Yellowstone's hot springs. He found a bacterium called Thermus aquaticus living in water near 70 degrees Celsius. Decades later, an enzyme taken from that bacterium became the key ingredient in a process called PCR, which stands for polymerase chain reaction. PCR allows scientists to copy tiny fragments of DNA very quickly. It is the same technology used in modern medical testing, forensic science, and the study of ancient DNA. A microbe from a boiling pool in Wyoming quietly changed the course of human medicine. That connection is worth sitting with for a moment. A creature smaller than a speck of dust, living in a remote thermal pool, held inside it a biological tool that humans would one day use to read the genetic code of life itself. The hot spring did not know it was contributing to anything. It was simply doing what it has always done, keeping its ancient passengers alive in the heat. The oldest living ecosystems on Earth may look like empty, steaming pools to a passing visitor. But look closer, in the way that science allows us to look, and you find entire cities of life. You find organisms that predate the dinosaurs by billions of years. You find chemistry so precise that it sorts living things by fractions of a degree. You find the deep past of our planet still alive, still working, still turning heat into life, one microscopic layer at a time. The water boils, the colors glow, and in the middle of all that heat, something ancient breathes quietly on. Beneath all of that color and life, beneath the boiling pools and the ancient microbes and the soft mineral shelves, something enormous is sleeping. Yellowstone National Park sits on top of one of the largest volcanic systems on Earth. Not a regular volcano, the kind with a cone and a peak. Something far bigger. Scientists call it a supervolcano, which means a volcanic system capable of erupting with a force many hundreds of times greater than any ordinary eruption in recorded history. The magma chamber beneath Yellowstone, the vast underground reservoir of molten rock that feeds every geyser and hot spring in the park, stretches roughly 55 miles long and 20 miles wide. It sits between 3 and 9 miles below the surface. You cannot see it. You cannot hear it. But you can feel its breath rising through every thermal feature in the park. Stand at the edge of the grand prismatic spring on a cool morning and look out across the water. The spring is enormous, nearly 370 feet across, which makes it the largest hot spring in the United States and the 3rd largest in the world. The steam rises in thick white columns, curling upward and drifting slowly across the surface. The center of the water is a deep, vivid blue, almost electric, the color of a tropical ocean seen from above. Moving outward from that center, the color shifts. It turns green, then yellow, then orange, then a deep rust red at the very edges. Those rings of color are not decoration. They are living organisms, mats of heat-loving bacteria arranged by temperature. Each band a different community of life, thriving at exactly the degree it prefers. The whole spring looks like a painting, something too precise and too vivid to be natural. But it is entirely natural. It is the surface expression of a supervolcano's slow, steady exhale. The ground around Yellowstone's thermal features is not flat or ordinary. It is sculpted by heat and chemistry into something that looks almost alien. In some areas, the earth is bright white, crusted with silica, a mineral that hot water carries up from deep underground and deposits on the surface as it cools. These silica formations, called sinter terraces, build up over thousands of years, layer by layer, like slow stone waterfalls frozen in place. They are pale and smooth, almost chalky to look at, and they spread out in wide, flat shelves around the vents and pools. In other areas, the ground is a pale yellow, stained by sulfur deposits left behind by rising volcanic gases. The sulfur gives off a faint smell, sharp and unmistakable, that visitors notice long before they see the source. At Mammoth Hot Springs, near the northern edge of Yellowstone, the surface looks completely different. Here, the hot water is rich in calcium carbonate, the same mineral found in chalk and limestone. As the water flows up and spreads across the hillside, it deposits this mineral in layers, building up terraced formations called travertine. The terraces at Mammoth are pale cream and white, sometimes tinged with orange or pink from the bacteria living in the water's edges. They cascade down the hillside in wide, shallow steps, each one holding a shallow pool of warm, clear water. From a distance, the whole formation looks like a frozen waterfall, or perhaps a wedding cake built by the earth itself over thousands of patient years. The ground in and around these thermal areas is also unstable in ways that are not always visible. The heat from below keeps the soil warm year-round. Even in the depths of a Wyoming winter, when snow covers everything else, visitors walking through Yellowstone in January sometimes notice patches of bare ground surrounded by deep snow, the earth too warm for the snow to stick. Steam rises from cracks in the soil. The frost never fully settles there. The land breathes. Yellowstone sits above what geologists call a hot spot, a place where a column of unusually hot material rises from deep within the Earth's mantle. The thick layer of hot rock beneath the crust and pushes heat toward the surface. The North American tectonic plate, the vast slab of rock that carries the continent, moves slowly over this hot spot over millions of years. The hot spot itself stays roughly in place. This is why the chain of ancient volcanic features stretches across the Snake River Plain in Idaho, a trail of old eruption sites left behind as the continent drifted over the heat source below. Yellowstone is simply where the continent sits above that heat right now. All of that ancient force, all of that deep planetary heat rises to the surface and glows in the colors of a spring, steams quietly from a crack in pale white ground, and feeds the oldest living things on Earth. The surface is calm. The depth is not. Geysers do not grow just anywhere. They need a very specific set of conditions, and most places on Earth simply do not have them. Of all the geothermal features in the world, geysers are the rarest. Hot springs exist on nearly every continent. Mud pots bubble in dozens of countries. But true geysers, the kind that shoot boiling water high into the air on a regular schedule, number only in the thousands worldwide. Scientists estimate there are roughly 1,000 geysers on the entire planet. About half of them Yellowstone. The reason geysers are so rare comes down to what lies beneath the ground. A geyser needs three things working together at the same time. It needs heat, and plenty of it. It needs water, moving steadily downward through the rock. And it needs a very particular kind of underground channel, one that is narrow, twisted, and sealed tightly enough to trap pressure. If any one of those three things is missing or slightly off, the geyser never forms. A hot spring appears instead, or nothing at all. The underground channels that feed geysers are called conduits. Picture a long, winding tube carved through solid rock, sometimes hundreds of feet deep. The walls of this tube are lined with a mineral called silica, which comes from a type of rock called rhyolite. Rhyolite is rich in silica, and when hot water moves through it, the silica slowly dissolves into the water. Over time, that dissolved silica coats the inside walls of the conduit and seals them. This sealing is essential. Without it, the pressure would simply leak away through the surrounding rock, and no eruption would ever happen. The silica acts like a natural pipe lining, built slowly over thousands of years. This is why geysers cluster in places where rhyolite rock is common. Yellowstone sits on enormous deposits of it. Iceland has it. New Zealand's Taupo volcanic zone has it. Chile's El Tatio geyser field, the highest geyser field in the world at over 14,000 feet above sea level, sits on it too. The rock itself is part of the recipe. Remove the rhyolite, and the geyser has no way to seal its own plumbing. The depth of a geyser's conduit also matters enormously. Water at the bottom of a deep conduit is under tremendous pressure from all the water sitting above it. That pressure raises the boiling point of water far above the normal 100 degrees Celsius. We know at the surface, deep underground, water can reach 150 degrees Celsius or higher and still remain liquid, held in place by the weight pressing down on it from above. It is superheated water, water that is far hotter than boiling, but has not yet turned to steam. This is the fuel stored in the Earth's underground chambers, waiting quietly in the dark. The shape of the conduit controls everything that happens next. Some conduits are wide and open at the top, superheated water simply rises, reaches a depth where the pressure drops enough, flashes to steam, and bubbles out gently as a hot spring. There is no drama, no eruption, just a quiet, steady flow. But when the conduit narrows near the top, something different happens. The narrow section acts like a bottleneck. The water below cannot release its pressure gradually. It builds and builds until the water near the top begins to boil, reducing the weight pressing down on the water below, which then flashes to steam all at once. The whole column erupts upward in seconds. Scientists who study geysers use instruments called temperature loggers and pressure sensors, lowered carefully into the conduit on thin cables, to map what is happening far below the surface. What they find is surprising. The underground plumbing of a geyser is never simple. It branches, it widens and narrows. It connects to side chambers that store extra water. Some geysers have what researchers call bubble traps, small pockets in the conduit where steam collects before each eruption, acting like a trigger. When enough steam fills the trap, it pushes water upward, starts the chain reaction, and the geyser fires. Every geyser is its own quiet machine, built slowly by heat and water and mineral-coated rock over centuries. No two are exactly alike. The conduit of Old Faithful looks nothing like the conduit of the Strákar Geyser in Iceland, which erupts every few minutes in a wide, dome-shaped burst of brilliant blue water. Each one found its own shape in the dark, carved by forces that never stop working. The surface shows you the result. The depths hold the reason. When a geyser finally erupts, your whole body knows it before your eyes do. The ground beneath your feet begins to tremble. It is a low, rolling vibration, like a distant truck passing on a highway, except it comes from everywhere at once. Visitors to Yellowstone often describe feeling it in their legs first, then in their chest. The earth is moving. Something enormous is waking up. Then comes the sound. Seconds before the water breaks the surface, a deep, hollow roar rises from the vent. It is not a sharp crack or a bang. It is more like a long, pressured exhale, the sound of superheated steam forcing itself through narrow rock passages at tremendous speed. Some geysers add a rhythmic chugging to that roar, a pulse that beats faster and faster as the eruption builds. Scientists believe this pulsing happens because steam and water are trading places rapidly inside the conduit, each surge pushing the column a little higher than the last. When the water finally breaks free, it catches the light in a way that is hard to forget. The column is not solid. It is a churning mix of liquid water and white steam, and sunlight passes through it differently at every height. Near the base, the water is dense and bright. Higher up, it dissolves into a wide, drifting cloud of vapor that hangs in the air long after the eruption peaks. On cold mornings, that cloud can rise hundreds of feet before it fades, glowing softly against a pale sky. The eruption itself follows a cycle that is as reliable as a tide. Old Faithful, the most famous geyser in Yellowstone, erupts roughly every 44 to 125 minutes. That wide range surprises some people. They expect a clock. What they get instead is something more like a breathing pattern, one that shifts slightly depending on how long the previous eruption lasted. A short eruption means the underground chamber did not fully empty, so the next eruption comes sooner. A long eruption empties the system more completely, and the geyser needs more time to refill and reheat. The two are linked. Each eruption shapes the one that follows. This is the rhythm of a geyser, not a metronome, but a living pulse. The water that shoots into the air is extraordinarily hot. At Old Faithful, the water temperature at the vent is close to 204 degrees Fahrenheit, just below the boiling point. At that altitude, Yellowstone sits at roughly 7,000 feet above sea level, and water boils at a lower temperature at high altitude because the air pressure is lighter there. This matters. It means the water inside the conduit, under the weight of the column above it, stays liquid at temperatures that would boil it instantly at the surface. The moment that pressure releases, the water flashes to steam and expands with tremendous force. That expansion is what drives the eruption upward. A single eruption of Old Faithful releases somewhere between 3,700 and 8,400 gallons of water. That water has spent years possibly decades, soaking slowly down through the rock, heating up and waiting. It travels back to the surface in under 2 minutes. The whole cycle, from the first trembling of the ground to the last wisps of steam drifting away, lasts only a few minutes. Then the vent goes quiet. The ground stills. The geyser begins to fill again. Smaller geysers have shorter, faster cycles. Stråkr in Iceland erupts every 4 to 8 minutes, throwing a wide dome of brilliant blue water about 65 feet into the air before it collapses back into the vent. Watching it is almost hypnotic. The surface of the pool swells, stretches upward into a glassy blue bubble, and then bursts over and over. The cycle never stops. What makes these rhythms possible is the stability of the heat source far below. As long as the magma chamber beneath the surface stays hot, and as long as groundwater keeps seeping down through the rock, the cycle continues. Heat rises, water falls, steam builds, the geyser fires. The system resets. It has been doing this for thousands of years in some places, long before any human being stood at the edge of a vent and felt the ground shake beneath their feet. There is something deeply calming about a cycle you can trust. The geyser does not hurry. It does not skip steps. It follows the same path every time, shaped by the same pressures, the same heat, the same narrow passages carved into the rock long ago. It simply waits. And then, when everything is ready, it rises. Around every geyser and every hot spring, the ground tells a story. Not in words, but in color. The earth near these thermal features is painted in shades that seem almost impossible for bare rock and soil. Rust red, pale yellow, bright orange, soft white. These colors come from minerals, and they are everywhere around geothermal areas, coating the ground like a slow and patient artist has been at work for centuries. The most common of these minerals is silica, a hard, glassy material that hot water pulls up from deep inside the earth. As the water cools at the surface, it drops that silica behind. Over time, layer by layer, the silica builds up into a smooth, pale rock called sinter. Sinter forms the wide, flat platforms you often see surrounding geysers. Those broad, pale shelves that look almost like frozen foam. The center around Old Faithful in Yellowstone is thousands of years old. Every eruption adds just a tiny bit more. Silica is not the only mineral making its mark. In some thermal areas, the water carries calcium carbonate, the same mineral that makes up chalk and seashells. When calcium carbonate builds up around a hot spring, it forms a rock called travertine. Travertine grows in flowing, rippled shapes, like frozen waterfalls or stacked shallow pools. Mammoth Hot Springs in Yellowstone is one of the most striking examples on Earth. The terraces there look like someone poured thick cream over a hillside and let it harden. The pale white and tan formations glow softly in the afternoon light, and warm water still trickles over their edges, slowly adding to what has been building for thousands of years. The yellow and orange colors you see near many hot springs come from sulfur. Sulfur is a bright, waxy mineral that smells strongly of rotten eggs. It forms near vents where volcanic gases rise to the surface, and it coats the rocks in vivid patches of gold and amber. Up close, sulfur crystals have a soft, almost powdery look. They are delicate. You could crush them between your fingers. Yet, they survive in one of the harshest environments on the surface of the Earth, sitting right at the edge of boiling water and scalding steam. Iron minerals bring the deep reds and rich oranges. When iron in the rock meets oxygen and water, it rusts, just the way a nail left in the rain turns brown and flaky. In geothermal areas, this process happens on a grand scale. The ground around some hot springs is stained in deep brick red and burnt orange, the colors spreading outward from the water's edge like a slow tide. At the Waiotapu Thermal Park in New Zealand, the ground shifts through so many shades of red, orange, yellow, and green that the whole area looks like a painting that cannot quite decide what color it wants to be. The green colors come from something different. Sometimes it is algae, the tiny living organisms that thrive in warm water. But sometimes it is a mineral called chlorite, a soft, flaky green mineral that forms in certain types of volcanic rock. The two can look similar from a distance, but one is alive and one is stone. Both are beautiful. What makes all of this so striking is that these minerals do not just sit still. They are always moving, always being carried, always being deposited somewhere new. The hot water is a slow conveyor, picking up minerals deep underground and bringing them to the surface. Every drop of water that rises through a geyser vent or seeps out of a hot spring carries a tiny, invisible load of dissolved rock. When that water cools or evaporates or splashes against the air, it lets go of what it was carrying. The minerals settle. The formations grow. Over hundreds and thousands of years, this process builds structures that look almost architectural. The travertine terraces at Mammoth Hot Springs grow about 2 inches per year in some places. The center platforms around geysers can be several feet thick. These are not fast changes. They are the kind of changes that ask for patience to appreciate. But they are real, and they are constant, and they are happening right now, in this moment, while everything else in the world goes on around them. The ground near a geyser is never just ground. It is a record. Every layer of sinter, every crust of sulfur, every ripple of travertine holds the memory of water that passed through long ago. Water that rose from deep inside the earth, gave up what it was carrying, and then flowed away. The land holds onto what the water leaves behind, and slowly, quietly, the colors deepen. The water that moves through these thermal systems is not ordinary water. It carries a chemistry all its own. And when scientists study it closely, they find some of the most extreme conditions found anywhere on the surface of our planet. Start with temperature. Most of us know that water boils at 212 degrees Fahrenheit. But the water deep inside a geyser's plumbing can reach temperatures far above that without turning to steam. This happens because of pressure. Deep underground, the weight of all that rock and water above pushes down so hard that the water cannot boil. Even when it is scorching hot, scientists have measured water in some hydrothermal systems at temperatures above 400 degrees Fahrenheit. Still liquid, still moving, still dissolving minerals from the rock around it. It is only when that water rises toward the surface, where the pressure drops, that it finally flashes into steam and erupts into the open air. Then there is the acid. Many hot springs carry sulfuric acid, formed when hydrogen sulfide gas from deep in the earth reacts with oxygen and water near the surface. Some of these acid springs have a pH close to 0. That is roughly as acidic as battery acid. The water looks clear, even beautiful, with a faint blue or green shimmer. But it can dissolve metal. It eats through rock. It strips color from everything it touches. Standing near one of these springs, you can smell the sharp bite of sulfur in the air, a smell like struck matches, drifting across the ground in thin, pale wisps of steam. On the other end of the scale, some hot springs are intensely alkaline, meaning the opposite of acidic. The hot springs at Mono Lake in California and certain pools in Yellowstone carry water with a very high pH, sometimes above 9 or even higher. This kind of water feels slippery to the touch, almost soapy. It too dissolves rock in its own way, pulling silica from deep volcanic stone and carrying it upward. When that silica-rich water reaches the surface and cools, it deposits the smooth white mineral called geyserite, building the pale, chalky platforms that ring so many geyser vents. Some thermal waters carry dissolved gases in concentrations that would be dangerous to breathe in an enclosed space. Carbon dioxide seeps from volcanic ground in some areas so heavily that it pools in low spots, invisible and odorless, and can suffocate small animals that wander into hollows where the gas collects. In certain parts of Italy, in a region called the Valley of the Dead near Pozzuoli, this phenomenon was documented for centuries. Birds and small creatures were found dead near the ground, while larger animals standing upright were unharmed. The Romans called it a cursed place. The explanation was simply chemistry. The dissolved mineral content of thermal water can also reach extraordinary levels. Some springs are so saturated with silica, calcium, or other minerals that they deposit material almost as fast as water flows through them. At Fly Geyser in Nevada, a small human-made well accidentally tapped a geothermal source in 1964. The minerals in that water have been building up ever since, forming a cone of bright red, orange, and green terraces that grows a little taller every year. The colors come from heat-loving algae and minerals mixing together on the surface. The structure looks like something from another world, and in a sense, it is. It is a record of 60 years of chemistry, written in stone. The silica in geyser water is also responsible for one of the more surprising facts about these systems. The sinter, that pale mineral crust around geyser vents, is essentially a form of opal, not the gem-quality opal found in jewelry, but the same basic mineral structure. Hydrous silica, silica with water locked inside its crystal structure. When geologists examine old geyser fields that have gone quiet, they sometimes find thick beds of this opaline sinter buried under later rock layers. These beds can tell scientists where ancient geothermal systems once existed, millions of years ago, long before any human eye was there to see them erupt. And perhaps the most extreme fact of all is simply the age of some of this water. Scientists, using isotope analysis, a method that reads the chemical fingerprints of water molecules, have found that some of the water rising through deep geothermal systems fell as rain or snow thousands of years ago. It soaked into the ground, traveled slowly downward through cracks in the rock, was heated by the Earth's interior, and is only now making its way back to the surface. The water in a hot spring today may have begun its underground passage during the last ice age. It has been moving through the dark, through the heat, through the stone, all this time. And now it rises quietly into the light. That water, ancient and patient, has been moving through the dark for thousands of years. And when it finally surfaces, it does not arrive unnoticed. Humans have been finding these warm, steaming pools for as long as our species has walked the earth. Hot springs have shaped where people settled, how they healed, what they believed, and even how entire civilizations grew. Long before anyone understood the geology beneath their feet, people recognized something powerful in a hot spring. The warmth was real. The minerals left behind on skin and stone were real. The steam rising in cold air was unmistakable. Ancient peoples across every continent built their lives near these places, drawn by the heat and the strange, mineral-rich water. In Japan, the tradition of bathing in natural hot springs is called onsen. It stretches back more than 1,000 years. Japanese culture built an entire philosophy around these baths, one of quiet rest and physical renewal. Today, Japan has more than 3,000 hot spring resorts, and the country sits on one of the most geothermally active zones on the planet. The same volcanic forces that make Japan's geology so restless also fill its mountains with warm, mineral-laden pools. The Romans were equally devoted. Roman engineers built elaborate bathhouses called thermae over natural hot springs across their empire. The city of Bath, in what is now England, was built around a single hot spring that produces roughly 1 million liters of water every day. The Romans called it Aquisules, the waters of the goddess Sulis. They believed the spring was sacred. They threw offerings into it, small tablets of lead and pewter, with prayers scratched into the surface, asking the goddess for help. Archaeologists have pulled thousands of these tablets from the spring's ancient basin. They are small, quiet voices from the past, preserved by the very mineral-rich water the Romans revered. Hot springs shaped medicine too. For centuries, physicians prescribed mineral baths for everything from joint pain to skin conditions. The word spa itself comes from a town in Belgium called Spa, which was famous across Europe for its mineral springs. By the 1700s, wealthy Europeans traveled great distances to sit in warm mineral water, believing it would cure what ailed them. Some of those beliefs were wishful thinking, but some had real basis. The sulfur, magnesium, and silica in thermal water do affect the skin. Studies have shown that bathing in certain mineral-rich waters can ease symptoms of conditions like psoriasis, a skin disorder that causes red, scaly patches. The ancient instinct was not entirely wrong. In Iceland, hot springs shaped an entire nation's relationship with energy. Iceland sits directly on the mid-Atlantic ridge, the long underwater mountain range where two of Earth's great tectonic plates pull slowly apart. This makes Iceland one of the most geothermally active places on the planet. Today, nearly 90% of Icelandic homes are heated using geothermal water pumped directly from the ground. The capital city, Reykjavik, has used this system since the 1930s. Pipes carry hot water from underground springs into radiators inside homes and buildings. The city stays warm through long, dark winters without burning coal or oil. A natural process, millions of years old, heats a modern city. Native American peoples across the American West held hot springs as sacred places long before European settlers arrived. The Shoshone people knew the Yellowstone region and its thermal features for centuries before any outside explorer set foot there. They understood these places as powerful and alive. Some groups used the hot springs for cooking. Others used the warm water for healing. The springs were woven into their stories, their ceremonies, and their understanding of the land. Even the earliest written records of human civilization mention hot springs. Ancient Greek and Roman texts describe thermal baths with careful detail. The Greek physician Hippocrates, who lived around 400 BCE and is often called the father of medicine, wrote about the healing properties of mineral water. He believed that bathing in natural springs could restore balance to the body. He was working without any knowledge of chemistry or geology, but his instinct that these waters were different, that they carried something the body could use, was not wrong. What is remarkable is how consistent this pattern is across cultures that never met. People in Japan, in Rome, in Iceland, in the American West, in ancient Greece, all found the same thing. They found warmth rising from the ground. They found water that tasted of minerals and left a soft residue on the skin. And they all independently decided this place was worth staying near. The earth was offering something, and people across every age and every continent quietly accepted. Animals found these places long before people did, long before any human set foot near a hot spring. Animals had already learned what the warm water offered. Bison in Yellowstone have gathered near thermal areas for thousands of years. The ground near hot springs stays warmer in winter. The snow melts faster there. The grass grows earlier in the season. For a large animal trying to survive a mountain winter, that patch of warm earth is not a small thing. It is the difference between finding food and not finding it. Elk do the same. They move toward the thermal basins when the cold deepens. They graze on the grasses that grow in the heated soil. Scientists who study Yellowstone's wildlife have noticed that the animals follow the heat with great precision. They know the land. They know where the warmth rises. They have been learning this for far longer than any written record can reach. Birds are drawn to hot springs too. In Iceland, where geothermal heat rises across the whole island, certain bird species nest near warm pools year-round. The water stays liquid even when the air is well below freezing. Ducks and swans float on steaming pools while snow falls around them. It looks almost impossible, but the birds are simply doing what animals have always done. They are reading the earth and responding to what it offers. In Japan, the Japanese macaque, a small, thick-furred monkey, has become one of the most photographed animals on the planet because of its relationship with hot springs. These monkeys sit in the warm water during winter snowstorms. They close their eyes. They look, by any honest description, deeply comfortable. Scientists have studied their behavior carefully. The warm water lowers their stress hormones. It helps them conserve body heat. The monkeys that use the hot springs survive harsh winters at a higher rate than those that do not. What looks like a monkey enjoying a bath is actually a finely tuned survival strategy shaped over many generations. This is how discovery often works. It does not begin with a scientist holding a notebook. It begins with something alive, following warmth, following instinct, following what the body already knows. When European explorers first arrived in what is now Yellowstone in the late 1700s and early 1800s, they brought back stories that almost no one believed. A trapper named John Coulter is often credited as the first non-Native American to see the thermal features of the Yellowstone region. He passed through the area around 1807 or 1808 when he returned and described what he had seen: the geysers and boiling pools and columns of steam. People called the place Coulter's Hell. They thought he was exaggerating. The idea of water shooting from the ground in a great column of steam seemed too strange to accept. It took decades before formal expeditions confirmed what Coulter and the native peoples of the region had always known. The Washburn-Langford-Doane expedition of 1870 was one of the first organized American efforts to document the Yellowstone region in detail. The men who went on that expedition were not geologists, not in the formal sense. They were surveyors, soldiers, and curious civilians. But they took careful notes. They measured. They sketched. They tried to describe what they saw in language that others could believe. Ferdinand Hayden led a more formal geological survey of the region in 1871. His team included a photographer named William Henry Jackson and a painter named Thomas Moran. The photographs and paintings they brought back changed everything. Suddenly, people could see it. The images showed the steam rising from the pools, the bright colors ringing the water, the great plume of Old Faithful climbing into the sky. Congress voted to protect Yellowstone as a national park in 1872, just 1 year after Hayden's survey. It was the first national park in the United States, and the thermal features were a large part of why people felt it deserved protection. The animals had known for thousands of years. The native peoples of the region had known for thousands of years. The formal scientific record took much longer to catch up, but when it did, when the photographs arrived and the surveys were published, and the geologists began to explain the plumbing beneath the ground, something important happened. The wonder that people had always felt near these places was given a new kind of language, not a better language than the one the animals use, or the one the old stories use, just a different one. Another way of saying, this place is alive, and it is worth paying attention to. The elk still graze near the warm ground. The macaques still sit in their steaming pools. The birds still nest where the water never freezes. They have not needed the scientific language. They have always understood the warmth directly. And yet the warmth does not belong to Earth alone. This is perhaps the strangest and most beautiful thing about geysers and hot springs. We think of them as features of our world. We picture Yellowstone, or the geothermal fields of Iceland, or the steaming vents along the ocean floor. We think of them as something our planet does. But the forces that drive them, heat, water, pressure, chemistry, not unique to Earth. They exist elsewhere in our solar system, and scientists have found evidence that geysers, or something very much like them, erupt on other worlds right now. Consider a small moon called Enceladus. It orbits Saturn, that ringed giant sitting nearly 1 billion miles from the Sun. Enceladus is only about 313 miles across. You could drive across it in a long afternoon. It is covered in bright white ice, and for a long time scientists assumed it was frozen solid and quiet. Then, in 2005, the Cassini spacecraft flew close and saw something no one expected. Enormous plumes of water vapor and ice crystals were shooting out from the moon's south pole, not small wisps. Tall, dramatic jets rising hundreds of miles above the surface and spraying material out into space. These plumes come from a liquid ocean hidden beneath the ice. The ocean sits under a shell of frozen water that may be tens of miles thick. Deep below that ice, the moon's rocky core is being gently squeezed by Saturn's gravity. That squeezing creates friction. Friction creates heat, and that heat warms the water from below, just as the magma beneath Yellowstone warms the water in its deep rock chambers. The mechanism is different in its details, but the principle is the same. Heat rises through water, pressure builds, and eventually something erupts. The plumes of Enceladus carry more than just water. Scientists analyzing the data from Cassini found hydrogen gas, carbon dioxide, and organic molecules. The basic chemical ingredients that on Earth are associated with life. Near the ocean floor of Enceladus, there may be hydrothermal vents, places where hot water meets cold rock and releases minerals and energy. On Earth, those same kinds of vents support entire ecosystems in the deep ocean, far from sunlight. Scientists now consider Enceladus one of the most promising places in the solar system to search for living things. Europa, a moon of Jupiter, tells a similar story. It too has a global ocean beneath a thick shell of ice. It too may have hydrothermal activity on its ocean floor. The ice on Europa's surface is cracked and streaked with reddish-brown lines. And scientists believe those lines are places where warm water from below has pushed up through the ice and refrozen. The moon is, in a quiet way, still moving, still active, still warm inside. Even Mars, which is cold and dry today, carries signs of a warmer past. Scientists have found ancient formations on Mars that look very much like the silica deposits left behind by hot springs on Earth. In 2015, researchers studying images from the Mars rover Spirit identified a large area of pale, bright rock that matched the chemical signature of silica. On Earth, that kind of silica forms in one of two ways: near hot springs or near steam vents where volcanic gases rise through the ground. Either way, it points to a time when Mars had liquid water, underground heat, and possibly the conditions for life. There is even evidence of geyser-like activity on Triton, a moon of Neptune, and on Pluto, where nitrogen geysers may erupt when sunlight warms the frozen surface just enough to turn solid nitrogen into gas. These are not water geysers in the way we think of them. They are driven by different materials and different forces, but they follow the same basic logic. A substance is heated, it expands, and it finds a way out. All of this changes the way we can think about the hot springs and geysers of Earth. They are not oddities. They are not rare accidents of geology. They are expressions of a process that happens across the solar system. Wherever heat and pressure and liquid come together, the same physics that sends Old Faithful climbing into the Wyoming sky also drives plumes of ice and vapor from the South Pole of a tiny moon circling Saturn. The same chemistry that colors the hot springs of Yellowstone in gold and orange may be happening right now at the bottom of an ocean, hidden under miles of alien ice. The warmth beneath the ground is not ours alone. It belongs to the whole solar system, and perhaps in the water of some distant moon, something is already paying attention to it. Here on Earth, a geyser field is never just a geyser field. It is a living system, and every part of it depends on every other part. Think about what a geyser actually needs. It needs heat rising from deep below. It needs water filtering down from the surface. It needs a network of underground channels and chambers to hold that water and focus the pressure. Remove any one of those things, geyser stops. The whole system only works because many different forces are cooperating at once, each one doing its part without knowing the others exist. That underground water does not appear from nowhere. Most of it falls as rain or snow on the land surrounding the geyser field. In Yellowstone, scientists have traced the water that erupts from Old Faithful back to snowmelt and rainfall that soaked into the ground years, sometimes decades, before. The water travels slowly through cracks in the rock, moving downward through layers of stone until it reaches the heat below. A single drop of water that falls on a hillside in Wyoming might spend 50 years underground before it finally shoots into the sky. This means the geyser is connected to the weather. It is connected to the seasons. A dry year with little snowfall means less water moving through the system. A wet year sends more water down into the rock. The eruption you see on a summer afternoon may have been set in motion by a winter storm that happened before you were born. The rock itself plays a role too. Geysers almost always form in places where a specific type of rock called rhyolite is present. Rhyolite is a pale, fine-grained volcanic rock that contains a mineral called silica. As hot water moves through rhyolite, it dissolves tiny amounts of that silica and carries it upward. When the water cools near the surface, the silica settles out and slowly coats the walls of the underground channels, making them smooth and watertight. Without this lining, the pressure would leak away through the surrounding rock, and the geyser could never build the force it needs to erupt. The rock is not just a container. It is an active partner in the process. The microbes living in the hot spring pools are part of this system too. Those heat-loving bacteria, called thermophiles, do not just sit there looking colorful. They change the chemistry of the water around them. Some species pull minerals out of the water and deposit them as solid material, slowly reshaping the edges of the pool. Others produce acids that eat into the rock, widening cracks and shifting the flow of water underground. The living things and the geology are constantly rewriting each other. One slow chemical reaction at a time. Even the atmosphere above a geyser field is part of the picture. When a geyser erupts, it releases not just water vapor, but also gases like carbon dioxide and hydrogen sulfide, that sharp rotnik smell that visitors to Yellowstone often notice. These gases rise into the air and eventually mix into the broader atmosphere. Over very long timescales, volcanic and geothermal regions have contributed to the balance of gases that make Earth's air what it is. The breath of the planet, in a small but real way, carries the signature of its hot springs. And then there are the animals. Bison and elk in Yellowstone gather near thermal areas in winter because the ground stays warm and the snow melts faster there. The warmth creates patches of exposed grass when everything else is buried under white. Predators follow the grazers. The thermal features shape where animals go, which shapes how the land is grazed, which affects which plants grow, which affects the soil, which affects how water moves through the ground. One warm patch of earth sends ripples outward through an entire ecosystem. This is what makes a geyser field so much more than a geological curiosity. It sits at the center of a web of connections, pulling in weather and rock and microbes and wildlife and atmosphere all at once. Every eruption is the result of dozens of systems working together, each one nudging the others in ways that are quiet and slow and mostly invisible. The geyser does not know any of this, of course. It does not plan or coordinate. It simply responds to the conditions around it. The way water always finds its level and heat always finds a way to move. But the result, that tall white column rising against a blue sky, is the product of the whole planet working in concert. It is geology and biology and weather and chemistry, all arriving at the same moment in the same place to do one simple, extraordinary thing. And yet, that extraordinary thing does not last forever. Geysers are among the most fragile features on Earth. They look powerful. They sound powerful. A column of boiling water and steam shooting 60 feet into the cold air feels like something that could go on for 1,000 years without pause. But geysers are surprisingly easy to silence. And once they go quiet, they almost never come back. The most common way a geyser dies is simple. Its underground plumbing gets blocked. The narrow channels and chambers that took thousands of years to form can fill with minerals over time. Hot water carries dissolved silica, a mineral that comes from the rock itself. As the water cools slightly near the surface, that silica settles out of the water and coats the walls of the underground passages. Layer by layer, year by year, the channel grows narrower. One day, the water can no longer move fast enough to build the pressure needed for an eruption. The geyser falls quiet. It may still bubble. It may become a hot spring. But the eruptions stop. This process is slow and natural. It has been happening since the first geysers formed. Scientists believe that most of the geysers that have ever existed on Earth are already gone, their channels sealed shut, their heat still present underground, but no longer able to find a way out. The ones we see today are the survivors, the ones whose plumbing has stayed open long enough for us to witness them. But nature is not the only force that silences geysers. People have done it too, sometimes without meaning to. In the early 20th century, towns near geyser fields in New Zealand drilled deep wells into the ground to pull up hot water for heating and electricity. It worked. The water was hot and plentiful, but the drilling changed the pressure underground. Water that had been feeding the geysers was redirected. One by one, the geysers of the Werrikei field in New Zealand went quiet. Dozens of them. Some of the most active geyser fields in the southern hemisphere fell silent within a few decades. The heat was still there. The water was still there. But the careful balance of pressure that made eruptions possible had been broken. Yellowstone has its own history of human interference. In the late 1800s and early 1900s, visitors sometimes threw rocks, coins, and trash into the hot springs and geysers. Some of the objects lodged in the underground channels and disrupted the flow of water. A few geysers that were active when the park first opened have not erupted since. The damage from a single afternoon of careless behavior can outlast the person who caused it by centuries. Earthquakes can silence geysers too, though they can also wake them up. When a large earthquake shakes the ground, it can shift the rock around underground channels, either opening new pathways or collapsing old ones. After a major earthquake in 2003, scientists noticed changes in geyser activity at Yellowstone, even though the earthquake center was nearly 2,000 miles away in Alaska. The ground shook gently in Wyoming, and some geysers changed their eruption patterns for months afterward. The Earth's systems are connected so deeply that a tremor on one side of a continent can nudge a geyser on the other. Some geysers go silent for reasons that scientists still do not fully understand. Steamboat Geyser in Yellowstone, the tallest active geyser in the world, went nearly 50 years without a major eruption between the 1960s and 2018. Then, without any clear explanation, it began erupting again, sometimes several times a month. What changed underground is not entirely clear. The water found a new path, or the pressure rebuilt, or some small shift in the rock opened a passage that had been closed. Steamboat reminded scientists that a geyser is never truly dead until its heat source is gone. That heat source, the magma sitting miles below the surface, is the one thing that does not change on a human timescale. It has been there for millions of years. It will be there long after every geyser we know today has gone quiet. New geysers will form in the future, in places where the plumbing is still being carved by water and heat. They will erupt for centuries, then fall silent, then perhaps wake again. The geyser does not mourn its own silence. It simply waits, and the earth, patient and slow and full of heat, keeps working. The water keeps moving. The minerals keep building. The pressure keeps rising. Somewhere underground, right now, the next geyser is forming. That water moving underground right now did not fall from the sky yesterday. It may have fallen decades ago. Some of it fell as snow on a mountain range many miles away, long before anyone alive today was born. It soaked into the soil, slipped between grains of rock, and began a slow, quiet descent into the earth. Scientists call this water meteoric water, meaning water that comes from the sky rather than from deep inside the planet. And in most geyser fields around the world, meteoric water is the main ingredient. The rain and snow that falls on the land around Yellowstone, for example, can take anywhere from 500 to several thousand years to travel down through the rock get heated by the magma below and return to the surface as a geyser eruption. The water you see shooting into the sky today may have begun its journey before the first European explorers ever set foot on this continent. This is one of the quieter wonders of a geyser field. The connection between sky and earth is not obvious. You stand at the edge of a hot spring and feel the warm mist on your face, and it does not feel like rain. But it is. It is ancient rain, transformed by time and heat and pressure into something entirely new. The surface of the earth and the deep rock below are in constant conversation, trading water back and forth across centuries. Light plays a role in this exchange in ways that are easy to miss. When snow falls on the mountains surrounding a geyser field, it does not all melt at once. It accumulates in thick white layers, reflecting sunlight back into the sky. Snow is remarkably good at reflecting light. Fresh snow reflects up to 90% of the sunlight that hits it. This reflectivity is called albedo, which simply means how much light a surface bounces back rather than absorbs. High albedo keeps the snowpack cold and intact for longer, which means the melt is slow and steady. That slow melt allows water to seep gently into the ground rather than rushing away as surface runoff. The deeper the water soaks, the longer its underground journey, and the more thoroughly it gets heated before it returns. When the snow does begin to melt in spring, the light changes everything. The sun climbs higher in the sky. The days grow longer. The angle of the light shifts, and suddenly the same snow that reflected so much energy begins to absorb it instead. Dirty snow, dusted with wind-blown soil or volcanic ash, has a lower albedo. It absorbs more light and melts faster. In volcanic regions, fine ash particles can settle on snowfields and darken them, speeding up the melt. This means that volcanic activity and snowmelt are quietly linked, each influencing the other in ways that ripple down into the geyser systems below. The water that reaches a geyser's underground reservoir carries something else with it: dissolved gases and minerals picked up along the way. Rainwater is slightly acidic because it absorbs carbon dioxide from the air as it falls. That mild acidity helps it dissolve minerals from the rock it passes through. By the time the water reaches the deep, hot chambers below a geyser field, it has been chemically altered by its long passage. The heat below then changes it further, stripping some minerals away and loading the water with others, particularly silica and calcium carbonate. These are the minerals that build the beautiful pale formations around geysers and hot springs. In a very real sense, those pale white and cream-colored mineral deposits are made partly from the sky. The light that falls on a geyser field also shapes what you see at the surface. The steam rising from a hot spring catches the morning sun and glows gold and white. In low winter light, the same steam looks blue and silver. The colors of the water in a hot spring shift depending on the angle of the sun and the depth of the pool. Deep, clear thermal pools appear a vivid, almost electric blue in direct sunlight. Because the water absorbs the longer red wavelengths of light and scatters the shorter blue ones back to your eye. The same process makes the sky blue above you. The hot spring and the sky are reflecting the same physics, the same behavior of light, just in different forms. Rain falls, snow builds, light melts the snowpack slowly and gently. The water descends for centuries. It heats. It rises. It erupts in a column of steam and vapor that catches the morning light and glows. And somewhere in that glowing column, there is water that last saw the sky 1,000 years ago, finally returning home. Not every thermal feature announces itself with a great column of steam. Some of them speak in quieter, stranger voices. Some of them gurgle. Some of them hiss. And some of them make a sound so deep and wet and slow that it seems to come from somewhere far below the world you know. Mud pots are among the most unusual features in any geyser field. They sit low in the ground, often in wide, shallow basins, and they bubble. Slowly, constantly. The mud inside them is thick and gray and pale, the color of wet ash, and it moves in heavy, rolling bursts that send small splashes of clay up into the air. The sound they make is unlike anything else in nature. It is a deep, soft, rhythmic plop, like something enormous breathing just beneath the surface. Each bubble rises from below, swells and breaks open with a low, hollow pop that echoes slightly across the quiet ground around it. Mud pots form when there is not enough water nearby to fill a full, hot spring pool. Instead, the rising steam and volcanic gases, especially hydrogen sulfide and carbon dioxide, mix with just enough groundwater to create a wet, acidic slurry. That acid slowly breaks down the surrounding rock into fine clay particles. The result is that thick, pale mud, constantly stirred by the gases rising through it. The mud itself is the rock, dissolved. The ground is slowly eating itself, one quiet bubble at a time. The temperature inside a mud pot can reach close to the boiling point of water. Even though the mud looks calm and almost gentle from a distance, the bubbles are not water boiling. They are gas pushing up through the thick clay from below. Scientists have recorded the sounds of mud pots and found that each bubble has its own low frequency, its own brief rumble that travels through the ground before it ever reaches the surface. The mud pot is not just making sound in the air. It is vibrating the earth beneath your feet. Fumaroles are different again. They are the driest of all the thermal features. Where a geyser has water and a mud pot has wet clay, a fumarole has almost nothing but gas and heat. It is an opening in the ground where volcanic gases escape directly into the air. The sound a fumarole makes is a hiss, a steady, pressurized, forceful hiss that does not stop. It does not pause or cycle. It simply pushes constantly, like a valve that has been left open. Stand near a fumarole, and the sound fills your ears completely. It is not loud in the way a geyser eruption is loud, but it is relentless. The gas coming out of a fumarole can reach temperatures far above the boiling point of water, sometimes several hundred degrees. The steam and sulfur dioxide and carbon dioxide rush out with enough force to leave mineral deposits around the vent opening, yellow and white crusts of sulfur that build up slowly over years. Those yellow rings are a kind of frozen record of every breath the fumarole has taken. The gases from fumaroles are the same gases that volcanoes release during eruptions, just at a much slower and gentler rate. A fumarole is, in a sense, moments. A volcano exhaling quietly between its larger moments. The same chemistry, the same heat, the same deep origin, just expressed in a long, slow whisper instead of a roar. Together, mud pots and fumaroles and hot springs and geysers form a kind of vocabulary. Each one is the earth expressing the same underground heat in a different way, depending on how much water is present, how much gas is rising, how porous the rock is, and how deep the heat source sits. The same magma chamber below Yellowstone, for example, produces all of these features within a few miles of each other. Walk across that landscape and the ground changes its voice with every step. Here it bubbles, here it hisses, here it roars upward in a column of white steam. Here it sits perfectly still and blue and deep and silent. The sounds of a geyser field are the sounds of a planet that is still alive and working. The slow plop of a mud pot is the sound of rock becoming something new. The hiss of a fumarole is the sound of heat finding its way out. And underneath all of it, too low for human ears to detect without instruments, the ground itself vibrates with the movement of hot fluids through ancient stone. The earth is always making sound. Most of it we simply never hear. But some of that sound, scientists have learned to listen to very carefully. And what they hear has taught them something remarkable. Geysers, for all their wild and explosive drama, follow rules. Quiet, elegant, mathematical rules. The earth, it turns out, is not random. Even its most dramatic outbursts run on a kind of hidden clock. Scientists who study geysers are called volcanologists and hydrothermal researchers. They carry sensitive instruments called seismometers, which detect tiny vibrations in the ground, far too small for human hands to feel. They lower temperature probes deep into geyser vents. They set up cameras that record every eruption day and night, through rain and snow and summer heat. Over months and years, they build up a picture. And that picture slowly begins to show a pattern. Old Faithful in Yellowstone is the most famous example of this hidden order. Its name is not just a nickname. It is a description. Old Faithful erupts roughly every 44 to 125 minutes, and scientists can predict its next eruption with an accuracy of plus or minus 10 minutes simply by measuring how long the previous eruption lasted. A short eruption lasting around 2 minutes means the next one will come sooner. A long eruption lasting 4 to 5 minutes means the next one will take longer to build back up. The math is simple. The reliability is stunning. A column of boiling water driven by ancient rock and underground pressure keeps better time than most people expect from something so wild. The reason lies in the geometry of the geyser's plumbing. After each eruption, the underground chamber empties. Cool groundwater seeps back in through the surrounding rock. The heat from below begins warming that water again. The time it takes to reach the boiling point depends directly on how much water was expelled in the last eruption. More water expelled means a longer recharge time. Less water expelled means a shorter wait. It is a simple equation. Input, heat, output, repeat. The Earth runs this calculation automatically every single time without error. Other geysers show similar patterns, though some are harder to read. Stråkr in Iceland erupts every 5 to 10 minutes with remarkable consistency, sending a blue-green bubble of superheated water skyward before it bursts into white steam. Steamboat Geyser in Yellowstone, the tallest active geyser in the world, is far less predictable. For decades, it barely erupted at all. Then, beginning in 2018, it began erupting dozens of times per year. Scientists tracked changes in the local groundwater system and found that subtle shifts in water flow through the surrounding rock had reset Steamboat's internal rhythm. The clock had not broken. It had simply been reset. This is what makes geyser mathematics so beautiful. The numbers are not imposed from outside. They emerge naturally from the physical system itself. Water, heat, pressure, and rock interact according to the same laws of physics that govern everything else in the universe. The same equations that describe how water boils in a pot on a stove also describe what happens 1,000 feet below the surface of Yellowstone. Scale changes. The principles do not. Researchers have found that the interval between eruptions can also be affected by distant earthquakes. When a large earthquake sends seismic waves rolling through the ground. Those waves can disturb the water inside a geyser's underground plumbing. Geysers have been known to change their eruption timing after major earthquakes thousands of miles away. The 2002 earthquake in Alaska, more than 2,000 miles from Yellowstone, caused measurable changes in several of the park's geysers within days. The ground is connected in ways that are easy to forget. A tremor on one side of a continent can nudge a water clock on the other. Modern researchers now use GPS sensors to measure tiny changes in ground elevation around geyser fields. When magma or hot fluid moves underground, the ground above it swells slightly, sometimes by just a few millimeters. These measurements, taken over years, reveal the slow breathing of the hydrothermal system below. The ground at Yellowstone has risen and fallen by inches over decades, tracking the movement of heat and fluid deep beneath the surface. It is a slow, fast pulse. Patient instruments, reading patient numbers, reveal a system that has been running its quiet calculations for hundreds of thousands of years. There is something deeply calming about this. The earth is not chaotic. It is complex, yes. But underneath that complexity, simple rules hold everything in place. Water seeks heat. Heat seeks escape. Pressure builds until it finds a path. And then it releases, and the cycle begins again. The same pattern over and over, measured in minutes or centuries, always following the same quiet logic. People have known about the healing power of hot springs for a very long time. Long before anyone understood the chemistry of thermal water, humans sought these warm pools out. They soaked in them. They built villages near them. They called them sacred. And in many ways, they were right to do so. Thermal water carries dissolved minerals up from deep inside the earth. Silica, sulfur, calcium, magnesium, and dozens of other elements ride the heated water to the surface. When a person soaks in a mineral-rich hot spring, those minerals touch the skin. Some are absorbed in small amounts. Others simply soften and soothe. The warmth itself relaxes muscles and eases tension in ways that plain warm water cannot quite match. The Romans built elaborate bathhouses over natural hot springs across their empire. In Britain, the city of Bath sits directly above a geothermal spring that has been flowing for at least 10,000 years. The Romans called it Aquisules, meaning the waters of the goddess Sulis. They built temples and pools around it. People traveled from across the empire to bathe there. The spring still flows today, pushing out about 1 million liters of water every single day at a steady 46 degrees Celsius. In Japan, the tradition of soaking in hot springs is called onsen, and it has been part of daily life for more than 1,000 years. Japan sits on one of the most volcanically active regions on Earth, where tectonic plates grind and shift beneath the islands. This activity heats enormous amounts of groundwater. Japan has over 3,000 onsen facilities fed by natural thermal springs. The water in each one carries a slightly different mix of minerals, depending on the rock it passed through on its way to the surface. Some springs are rich in sulfur. Others carry iron or sodium bicarbonate. Each one feels and smells a little different. Modern medicine has studied the effects of balneotherapy, which is the practice of bathing in mineral-rich thermal water for health purposes. Research suggests that soaking in certain thermal waters can reduce inflammation and ease the pain of conditions like arthritis. The warmth increases blood flow near the skin's surface. The minerals may interact with the body in subtle ways that scientists are still working to understand fully. The results are not dramatic cures, but the relief is real enough that thermal bathing remains a common medical treatment in parts of Europe and Japan. What makes all of this possible is a system so precisely tuned that it almost seems impossible. Water must fall as rain or snow. It must sink into the ground through cracks in the right kind of rock. It must travel deep enough to be heated by the Earth's internal warmth, but not so deep that it never returns. The rock must be porous enough to hold water, but structured enough to channel it. The heat source below must be close enough to warm the water, but not so violent that it destroys the plumbing. Every variable must fall within a narrow range. The temperature of the water matters enormously. Water that reaches the surface at around 37 to 40 degrees Celsius, close to human body temperature, feels perfectly comfortable and draws people in. Water above 60 degrees can cause burns. Water below 20 feels like a cold stream. The springs that humans have cherished for centuries tend to fall in that gentle middle range, warm enough to soothe, cool enough to be safe. The chemistry must also be right. Water with too much sulfur can irritate the skin and lungs. Water with too much arsenic is toxic. But water with the right balance of dissolved minerals, carried gently to the surface over years of slow travel through rock, becomes something that feels almost like a gift. The earth, in its slow and complex way, filters and heats and delivers this water with a precision that no human system has ever quite matched. It is worth sitting with that for a moment. The same forces that drive volcanic eruptions and split continents apart also produce these quiet, warm pools where a person can rest. The same heat that melts rock miles below the surface rises gently enough in the right places to warm a shallow pool to the perfect temperature for a tired body. The earth does not intend any of this. It follows physics and chemistry and the slow logic of pressure and heat. But the result in certain places is something that feels almost kind. A warm pool in a cold landscape. Mineral water rising from ancient rock. The deep interior of the planet, offering something gentle to the surface above. Far from any shoreline, in the coldest and darkest parts of the ocean, the same forces are at work. The same heat rising from deep inside the earth. The same water finding its way through cracked rock. The same chemistry of minerals and pressure and temperature. Only here, the hot springs don't bubble up into open air. They open into the black water of the deep sea, miles below the surface, where no sunlight has ever reached. These underwater hot springs are called hydrothermal vents. Scientists first discovered them in 1977 near the Galapagos Islands in the Pacific Ocean. Before that discovery, most scientists believed that life could not exist without sunlight. Every food chain they had ever studied started with the sun. Plants use sunlight to grow. Animals eat the plants. Other animals eat those animals. The sun was the engine at the start of everything. That was the rule. And then the vents changed it. Around those first hydrothermal vents, researchers found entire communities of living things. Tube worms as long as a person's arm. Pale crabs moving slowly across the seafloor. Clusters of mussels and shrimp and fish, all gathered around the warm, mineral-rich water pouring out of the rock. None of them needed the sun. They were living on chemistry instead. Bacteria near the vents pull energy from hydrogen sulfide, a chemical in the vent water, and use it to make food. Other creatures eat those bacteria. A whole ecosystem running entirely on heat from the Earth's interior. Scientists call this process chemosynthesis. It is the opposite of photosynthesis, which uses sunlight. Chemosynthesis uses chemical energy instead. The discovery of chemosynthesis rewrote what scientists thought was possible for life. It opened up new questions that researchers are still working through today. One of the biggest questions is how widespread this kind of life might be. Hydrothermal vents have now been found in every ocean on Earth. The Mid-Atlantic Ridge, the Indian Ocean, the Arctic. Each vent field hosts its own community of creatures, some found nowhere else on the planet. Scientists believe there are many more vent fields still waiting to be found. The deep ocean floor is one of the least explored places on Earth. More humans have walked on the surface of the moon than have visited the deepest parts of the sea. The vents themselves come in different forms. Some release water that is extremely hot, above 400 degrees Celsius in some cases. These are called black smokers because the mineral-rich water billows out in dark plumes that look like thick black smoke rising through the water. Other vents release cooler, lighter water and are called white smokers. The minerals they carry are different, and the communities of life around them are different too. Scientists are still mapping these differences and trying to understand why certain creatures prefer certain vents. There is also the question of how life at the vents began. Some researchers believe that hydrothermal vents may have been the birthplace of the very first life on Earth. The warm, mineral-rich water, the chemical energy, the protected environment deep in the ocean, away from the harsh conditions at the surface billions of years ago. It is a theory, not a certainty, but the evidence is taken seriously by many scientists who study the origins of life. The vents may not just support life today. They may have started it. That possibility reaches far beyond our own planet. Scientists have found strong evidence that Europa, one of Jupiter's moons, has a liquid ocean beneath its thick shell of ice. Enceladus, a moon of Saturn, shoots jets of water vapor into space from cracks in its surface, suggesting a warm ocean below. If hydrothermal vents can support life without sunlight, deep in the cold ocean of Earth, then the same thing might be happening right now beneath the ice of those distant moons. The same chemistry, the same heat rising from a rocky interior, the same dark water, warm and mineral-rich, possibly hosting something alive. These are open questions. Scientists do not yet have the tools to reach those oceans and look. But the questions themselves are extraordinary. A hot spring on the floor of the Pacific Ocean, discovered less than 50 years ago, now sits at the center of one of the biggest mysteries in science. What else is alive in the universe? And where is it hiding? The Earth's heat does not stop at the shoreline. It rises through the seafloor just as it rises through the land. It warms the deep water just as it warms the pools of Yellowstone or Iceland. The same slow, steady force, reaching everywhere, making things possible in the dark that we are only beginning to understand. That slow, steady force does not just warm the water. Over time, it reshapes the land itself. Thermal features are not passive things sitting quietly in a meadow. They are active agents. They dissolve rock. They deposit minerals. They open new cracks and seal old ones. They are constantly, patiently rewriting the ground beneath them. Silica is one of the most common minerals that hot water carries to the surface. As the water cools and spreads across the ground, the silica settles out and hardens into a pale, smooth rock called sinter. Around the edges of many hot springs and geyser vents, you can see wide, flat shelves of this material, cream-colored and slightly glassy, built up layer by layer over thousands of years. The terraces at Mammoth Hot Springs in Yellowstone are made of a different mineral, calcium carbonate, which forms a white and orange rock called travertine. These formations look almost like frozen waterfalls, pale and layered, stacked in soft curves down the hillside. They grow slowly. A single centimeter of travertine can take years to form, but given enough time, they build into structures that are genuinely enormous. Over thousands of years, this steady mineral deposit changes the shape of the land in ways that are hard to undo. The ground around an active geyser field becomes coated, sealed, altered. Old stream beds get filled in. New channels form where the water finds lower ground. The soil chemistry changes so completely that only certain plants can grow there. And even those plants are specialists, adapted to acidic, mineral-heavy ground that would kill most ordinary vegetation. The land around a geyser field looks like nowhere else on Earth. And that is because it has been slowly remade by forces that most landscapes never experience. Now think forward. Not just thousands of years, but millions. The tectonic plates, those enormous slabs of rock that carry the continents, are always moving. They move about as fast as a fingernail grows, but over millions of years, that adds up to enormous distances. The hot spot beneath Yellowstone has actually stayed roughly in place, while the North American plate has drifted slowly over it. Scientists can trace a chain of ancient calderas, collapsed volcanic craters, stretching across Idaho and into Oregon, each one marking a place where the continent once sat above the same deep heat source. In roughly 2 million years, if the plate continues moving at its current pace, the hot spot will sit beneath a different part of the continent entirely. Yellowstone's geysers will quiet down. New thermal features may rise somewhere to the northeast. This is not a catastrophe. It is simply how the Earth works. Heat finds new paths. Water follows new cracks. The land is always in the middle of becoming something it has never been before. On a longer timescale still, the continents themselves will merge again. Scientists believe that roughly 250 million years from now, the major land masses will come together into a new supercontinent, sometimes called Amasia or Pangaea Proxima. When continents collide, they push up mountain ranges and create new zones of volcanic activity. New hotspots will form. New geyser fields will rise in places that are today flat ocean floor. The thermal features of the far future will be just as real and just as active as the ones steaming quietly in Yellowstone right now. They will just be somewhere else entirely. Even further out, the sun will slowly grow brighter and warmer over the next billion years. The surface of the earth will become hotter. The oceans may eventually begin to evaporate. But deep underground, the heat from radioactive decay, the slow breakdown of elements like uranium and thorium inside the Earth's core and mantle, will continue for billions of years. Beyond that, the interior of the Earth will stay warm long after the surface has changed beyond recognition. As long as there is heat below and water above, the conditions for hydrothermal activity will exist in some form. What is remarkable is how consistent this process has been. Geysers and hot springs have existed on Earth for billions of years. Ancient hot spring deposits have been found in rocks more than 3 billion years old, from a time when the planet looked almost nothing like it does today. The same basic process, heat rising through rock, water moving through cracks, minerals dissolving and redepositing, has been running continuously across deep time. The land changes around it. The continents move. The climate shifts. But the heat keeps rising, and the water keeps finding its way down, and the ground keeps being slowly, quietly remade from below. That same quiet, steady heat rising from the ground has caught the attention of engineers and scientists around the world. They see something remarkable in it. The Earth itself is a power source. And unlike the sun, which sets each evening, or the wind, which comes and goes, the heat inside our planet never stops. It has been running for 4.5 billion years. It shows no sign of stopping. Geothermal energy, which simply means energy drawn from the Earth's own heat, is already powering entire countries. Iceland sits directly on the Mid-Atlantic Ridge, the long underwater mountain chain where two of Earth's great tectonic plates slowly pull apart. That pulling creates enormous amounts of volcanic heat near the surface. Iceland taps that heat directly. Today, geothermal energy provides nearly all of Iceland's home heating and a large share of its electricity. The country runs almost entirely on the warmth rising from below its feet. Iceland is not alone. Kenya draws significant power from the Rift Valley, a place where the African continent is slowly being pulled in two. The ground there is thin and hot, and deep wells bring steam to the surface to spin turbines and generate electricity. The Philippines, El Salvador, and New Zealand all draw meaningful portions of their power from the Earth's interior. These are not experimental programs. They are mature, working systems that have been running for decades. What makes geothermal energy so striking? When you step back and look at it clearly, is where it comes from. The heat inside the Earth is not just leftover warmth from the planet's formation, though some of it is. A large portion comes from radioactive decay, the slow, steady breakdown of elements like uranium, thorium, and potassium deep inside the mantle and crust. These elements were forged inside ancient stars that died long before our sun was born. When those stars exploded, they scattered their material across space. That material eventually gathered into a cloud, and that cloud collapsed into our solar system. The Earth formed from it, and the radioactive elements inside those long-dead stars are still releasing energy today, warming the ground beneath your feet, feeding the geysers, heating the springs. The energy in a hot spring is, in a very real sense, starlight from another age. Scientists and engineers are now working to expand geothermal energy far beyond the places where volcanic heat sits close to the surface. New drilling technology allows wells to reach much deeper into the crust, into rock that is hot even without nearby volcanic activity. Almost anywhere on Earth, if you drill deep enough, the rock becomes hot. The question has always been how to bring that heat to the surface efficiently. Enhanced geothermal systems, a newer approach still being developed and tested, involve pumping water down into hot, dry rock, letting it absorb heat, and then drawing it back up as steam. Early projects in the United States, Europe, and Australia suggest this approach can work. If it scales up, geothermal power could become available almost anywhere on the planet, not just in volcanic regions. The total heat stored inside the Earth is almost impossible to picture. Scientists estimate that the thermal energy contained within the top 10 kilometers of the Earth's crust alone is many thousands of times greater than all the energy in every coal, oil, and gas reserve ever discovered. The Earth is not running low on heat. It is, by any human measure, essentially inexhaustible. There is something quietly moving about this. For all of human history, we have burned things to stay warm. We burned wood, then coal, then oil. We have always looked outward for energy, to the surface, to the sun, to the wind. But the Earth has been offering something else all along. A slow, patient warmth rising from deep inside the planet. The same warmth that feeds the geysers of Yellowstone. The same warmth that keeps the hot springs of Iceland steaming through the long winter dark. The same warmth that billions of years ago may have helped create the conditions for the first living things to appear on this planet. The geyser erupts, and the steam rises, and the water falls back to the ground and begins its slow journey downward again. It will take years to return, but it will return. The heat will still be there. The rock will still be warm, and the water will rise again, as it has for longer than we can truly imagine. We live on a planet that is alive with heat. It moves beneath us every moment of every day. It has shaped everything we see, and quietly, steadily, it is still shaping what comes next. Close your eyes for a moment and think about what lies beneath you right now. Not the floor, not the foundation of a building. Deeper than that. Miles and miles of solid rock pressing down on itself, growing hotter as it goes. And deeper still, a core of iron so hot it glows, spinning slowly at the center of everything. You cannot feel it, but it is there. It has always been there. The Earth is not a cold, still stone drifting through space. It is warm. It breathes. Not the way you breathe, with lungs and air and rhythm you can count. It breathes the way old things breathe. Slowly, over millions of years. A long exhale that takes the shape of a geyser. A quiet inhale as rainwater sinks back into the ground. We have spent this whole night together learning about that breath. We have watched steam rise from the surface of Yellowstone in the pale morning light. We have followed water as it sank through cracks in the rock and traveled down into the dark, where the heat of the planet waited for it. We have seen that water come back up, changed, carrying minerals, carrying warmth, carrying the memory of a journey that took decades to complete. We have looked at the colors of hot springs, that deep, impossible blue at the center, the rings of orange and yellow where the water cools, and the tiny living things called microbes begin to grow. Those microbes are some of the oldest forms of life on Earth. They were here long before the dinosaurs, long before the first fish, long before the first breath of oxygen filled the sky. They live in water that would kill most things, and they are still here, still glowing in their quiet rings of color. We have learned that geysers exist on other worlds, that a small moon of Saturn called Enceladus shoots plumes of water, ice, into space from cracks in its frozen surface, that somewhere out there, in the dark and cold of the outer solar system, heat is still doing what heat does. It rises. It finds a way. Everything we have talked about tonight points to the same quiet truth. The universe is not random. It is not cold and indifferent. It is full of systems that connect to each other, that feed each other, that keep each other going. The heat inside the earth feeds the geysers. The geysers feed the minerals into the soil. The minerals feed the microbes. The microbes helped feed the first complex life. And here you are, billions of years later, lying still, breathing slowly, a small warm creature on a small warm planet. That is not a small thing. Right now, somewhere in Yellowstone, Old Faithful is building pressure. The water in its deep channel is growing hotter. In a little while, it will erupt. A tall white column of steam and water rising into the cold night air. And then it will fall back. And the cycle will begin again. It has done this thousands and thousands of times. It will keep doing it long after any of us are here to watch. Right now, in Iceland, a hot spring is steaming softly under a sky full of stars. The northern lights may be moving overhead, green and slow, like something breathing. The water is warm. The air is cold, and somewhere nearby, someone is probably asleep. Right now, at the bottom of the ocean, a hydrothermal vent is pouring hot, mineral-rich water into the deep dark. Strange creatures live there. Tube worms and pale crabs and tiny shrimp that have never seen sunlight. They do not need sunlight. They have heat. They have chemistry. They have everything they need. The planet is alive with all of this, every second of every night. And you are part of it. Your body is warm for the same reason the earth is warm. Energy held inside, slowly released. You breathe. The planet breathes. Everything is moving, even now, even in the stillness of this moment. Let that stillness hold you. The rock beneath you is old and solid and patient. The sky above you is wide and full of light that has traveled unimaginable distances just to reach this moment. You are resting on a living world, in a turning galaxy, in a universe that has been building toward this quiet moment for longer than numbers can say. You are safe. You are small. And that is a wonderful thing to be. Subscribe for a brand new Earth topic every night. One tap, and something wonderful is waiting for you tomorrow. Sweet dreams.